All right, well, I guess on behalf of Nagar and Mac, I'd like to welcome you all here to our workshop here at RSS 2021. So today our workshop's on perception and control for autonomous navigation in crowded dynamic environments. So, this is kind of inspired by just trying to get robots out in the real world, moving around people in complicated situations. So whether it's a mobile robot, driving around a building, delivering packages, or an autonomous vehicle. So we've tried to bring, people from, we have a good variety of speakers today, both on the perception side and computer vision, as well as, robotics, control, and looking at people that also, combine those two areas. We've also tried to draw some participation from both industry and academia, and across, the ranks. So from, students through professor. So I think we have a good, exciting lineup of speakers today that we're excited to get into. So let me just share my screen real quick. So our schedule for the day is it's like this. So all these times here are in Pacific time. So feel free to adjust to your local time zone as needed. So we're starting out with our introductory welcome. Then we had 3 pre-recorded speakers who I guess were kind enough to record videos, send them to us, and we have up on our YouTube channel. So if you haven't had a chance to watch those already, hopefully the discussion that will follow this will inspire you to go watch those. After that, we're gonna have a short break, followed by live talks and a panel with 5 other additional speakers. And then we have some solicited talks, these lightning talks, and a poster session follow that. So that's we kind of have 3 chunks for our day. So I guess with that, why don't we get started? So our first panel here is with the speakers from the pre-recorded talks. So we have Alosha Osep, who is a postdoc at the Technical University of Munich. His background is mostly on the computer vision, perception, and tracking side. We also have Michael Koval, who's a senior software engineer at Waymo, who's working more on the planning and control side of things. And then we also have Alyssa Pearson, who's an assistant professor at Boston University. Yes, I can't see the current list of participants. So I'm not sure if she is here, since she at least will be on maternity leave very soon if she is not already. All right, so I guess, I don't see her here. But Alosha and Michael are both around. So the way we kind of envisioned these panels working is, I have a few prepared questions that I can ask, but so I can start out with those, and then we can invite questions from the audience as well. So be ready to ask about things. All right. So I guess, well, thanks for Alosha and Michael for taking the time to be here with us today and for preparing those talks. It was all really interesting. So one of the main things that kind of struck me in listening to both of your talks was, all 3 of the talks really, was kind of the idea of what modules and concepts you want to separate and which things you want to do in parallel or connect together. Like in Alosha's talk, you were talking about how you're doing segmentation and tracking together as one unified approach rather than separating it out into 2 distinct modules. And with Michael's talk, it was similar. You were taking behavior prediction and planning, which used to be 2 separate things, and then trying to fuse those together into one kind of larger problem that you're trying to solve. And by doing so, you're able to achieve better results. And Alyssa's talk also had a very similar fusion of behavior prediction and planning. So I guess my question for both of you is, how do you kind of decide which modules or ideas you want to connect and which things should stay separated, and kind of where it's kind of a blurry line? Is this kind of based on experience, guessing and checking, or are there more informed principles that you're using to do these separations?
Happy to take a stab at it first. Thanks for organizing, by the way. Appreciate the opportunity to present on some of the stuff we've been doing recently. Mm-hmm. Yeah, I guess I don't know that there's a silver bullet. I guess I can talk through some of the factors that we consider. One advantage of, I guess, what are the pros and cons? The pros of merging things is that you often get better performance if like the joint problem allows, like if that API between the two modules is lossy, which at least in prediction and planning it is. You also get, in some senses, a simpler system because you have fewer components to sort of worry about. Like it's conceptually simpler, often it's simpler in code because you don't end up with as much duplication. And sometimes it's easier to evaluate. Like you can imagine that evaluating like ADD behavior in interactive situations is actually quite hard if the behavior predictions don't reflect the interaction. And I guess the downsides are that like I know I said it's simpler, but in other ways it's more complex because like it requires more computation, or there's more ways that like a learned model can get it wrong. There's also a scalability hit where a very practical issue in industry is like you can have a team of person work on module A and a team of person work on module B, and those two groups don't need us to talk as much. And like if communication is quadratic in the number of people, like that is a pretty big speed up. It's like going from, you know, bubble sort to like radix sort or something. So like that's a pretty big efficiency boost. And finally, sometimes it makes the evaluation problem easier to split them, where if you have separate modules, you can evaluate them as a subcomponent, and errors in one module don't necessarily propagate to the other. So I know that basically those pros and cons are contradictory, and that's, I think, why it's hard, is that like which set of pros and which set of cons is worth it given the maturity of the system, the size of the team working on it, and your ability to define a meaningful API boundary between the two. And by meaningful there, I really mean your ability to evaluate it. Like how much can work on one group be decoupled from work done by another group? So I guess those are the considerations I'd say. And I'm hoping the other panelist has a silver bullet, because I would love to use it.
Yeah, so thank you for this question. I think it's a great question, but unfortunately, I don't really have a silver bullet here either. So I have to say that from the point of view we were going for here when fusing detection, segmentation, and tracking was that, in my view, this was always like a one thing to do, right? The reason why we in the past did that differently, like process each image or scan independently and then connect those across time, was just that it was easier to approach this problem in this way from several points of view. From like one of the reasons was definitely that computer vision is a very difficult problem, and we were still in the process of kind of figuring things out, right? So first we figure out how to detect objects and segment objects in images, and now we are figuring out how to do that directly in videos, right? So this is reason number one. Reason number two, I would definitely say it's also compute. So I don't imagine how we could train these networks that I was talking about that do detection, segmentation, spatial temporal level. I don't imagine how we would do this a few years ago, really. So there are like a few things here that came together and enabled to do this. And here also, I have to say that we had the same observation as Michael. So performance was simply much better when we could approach this holistically, right? But on second hand, I definitely can say that as Michael already mentioned, we kind of lose a bit of ability of investigating all components independently, right? So it becomes a bit more blurry of if there is a failure, what component is responsible for that. So I still see pros and cons here, and I don't really have a general answer for this, unfortunately.
Yeah, I mean, I think if any of us had a general answer, we would, be be pretty rich. So, but no, this is, I think, yeah, no, it's a hard question to kind of decide what to do. But thanks for sharing. Yeah, and I guess another kind of commonality I saw between both of your, I guess all three of the presentations was also on the idea of kind of aggregating information over time. On kind of your end, Alyosha, you were starting from kind of the raw sensor data, getting to this point of getting objects and then tracking those objects over time to get like kinematics. And then that kinematics was basically the input to the, planning and control side of things for Alyssa and Michael. So they're looking at the instantaneous kinematics, looking at that over time to get, measures of prediction, behavior, like how aggressive is it going to be, etc. And then using that to try to predict future actions to plan and control. So we have this kind of long chain of sequences here, where the kind of interface between the perception side and the planning and control side seems to be the stage of like kinematics. But I guess in both of your works, you looked at aggregating information over a sliding temporal window. So I mean, which I think is kind of an interesting idea and makes a lot of sense. But is there kind of any particular way that you pick the right time scale for either of those things? Again, was it more like guess and check? Were there guiding principles, or some combination of the two?
So in our case, this was purely empirical. So we were making experiments with what we get out with different temporal window sizes, and we just determined the optimal value here. And it was also kind of interesting that we observed here that by increasing this temporal window from like a single scan to a small temporal window, we observed very large gains here. And it saturated quite quickly. And I have to say that it's not entirely clear why this saturation happened. We had several theories from starting with this Gaussian assumption that we made, we modeled instances as Gaussians, right, might not really hold true on a larger temporal span, right? I think the distribution kind of quickly becomes multimodal. So I think this was one reason. The second reason, it also might be that we still have certain hardware limitations here, because we also had to do some subsampling when we were like when we were looking at a sequence of LiDAR scans, we had to sample points, right? And if we had more memory and we could skip the sampling part, then it might be that that we could also go with larger temporal windows. But I think that in our case, at least, the main takeaway was even with short temporal windows, the advantage or the gain is really very large.
Yeah, I'd say a very similar thing, that it's mostly empirical. I'd say that I'd say most questions, if you can make a question empirical, it's probably best to make it empirical, because that's probably how you're going to get the best results on the actual problem you're trying to solve. But I guess the one aspect that I touch on, and maybe is a little bit different in prediction, is I think there is sort of a fundamental difference between what happened in the past in the world, like in real life, and what like you plan to do in the future, because there's no, because of causality, there's no way other agents could possibly have access to that information. And I think that's one place where we are a little bit careful to think about the sort of the time horizons differently, about like how far in the past do you have to know to be able to predict what agents will do in the future, and then like how much information about sort of your own ego intent is there and like what you plan to do in the future, and they're somewhat different. And I guess the other point I'd make is that there's, I think, a bit of a a blurry line, just like how there's a blurry line between prediction and planning, a similar blurry line between like prediction and sort of tracking, where like behavior prediction really is just, you think of it as a really good like motion model for a tracker. And I think that again comes to many of the practical considerations of like, where's a useful place to draw that boundary so you can do productive work on the two components separately.
Yeah, thanks. Yeah, so I guess we're kind of getting to the end of the time we had allocated for this, but I guess I wanted to allow for one or two audience questions as well. Does anyone have a question that they would like to ask either of the panelists about their talks or more in general? I guess don't see anything coming in, any hands raised or anything coming in the chat or anything. Right. I guess maybe I can ask one last quick question, and then we can wrap up the session here. So I think both of you have talked about issues of scalability in the work, scaling up to large numbers of objects, scaling up to many different agents, particularly in trying to model their complex interactions in the future prediction. Do you think that the main things that are going to help with that is just kind of improved computational capabilities, improved algorithms, trying to take advantage of sparsity in interactions or things like that? Or are there any, I guess, how do you think scalability should or will be addressed over the coming years?
I guess scalability means a lot of different things. I guess like one type of scalability would be like the sort of capacity of the model, amount of data it can productively consume. And there I feel like there's a lot of really exciting work in ML research on scaling with more data. Like I've been really impressed with transformers, but I'm sure that's even old news now for folks who know more about the state of the art in ML. And then for scalability with sort of more practical scalability, as in like getting it applied to larger problems, I feel like there's really no substitute for just like having it used more in practice and seeing what organizations grow up around it. Like Conway's law is unfortunately real. So like a big part of the problem is like how do you figure out how to integrate that type of model into a full system that like you can actually maintain when it's solving a problem. And I think like at least I know that like people have figured this out obviously in a lot of domains, and I think we're figuring it out in many problem areas, but like there's still sort of clearly ways we can be more efficient.
Yeah, so my view on this topic is I think scalability comes with more compute and data, but here's a very important thing here is that we cannot keep scaling up supervised learning, right? Because this would mean that you would have to just annotate more data, more classes, more situations, and this is not really possible. I think we already exhausted here, kind of exhausted our resources when it comes to labeling. So I think the most important part here will be to figure out how to learn in unsupervised manner. And there was a lot of fantastic work in vision domain and other domains as well done recently. I'm also very excited about all these recent developments in the field of machine learning, about transformers, about recent methods for contrastive based on supervised learning. But the reason why I am a believer in scaling based on more data and compute is the NLP community. So there, I think we could really see that by figuring out how to train big models, transformers, namely transformers, in unsupervised manner, things just kind of took off there. So nowadays, state-of-the-art NLP models work amazingly well. We are not there in vision yet, and in most of other fields as well not, but I'm optimistic that we will get there. So definitely there's one big difference between, if I just compare NLP and vision, is that in NLP, input is kind of structured, right? We can scrap text from a web, we can split tokens into words, and it's like much easier to formulate pre-task tasks for unsupervised learning, right? In vision, this is difficult because to just split videos and images into basic units, such as objects, this is already a learning problem, right? So I think here there are more things that we still have to figure out, but I really believe we will get there.
All right. Thanks. All right, so let's all thank the speakers for their talks and participating in the panel. So, all right, and I guess with that, we're a little bit over time on the break, but we can jump into the live talk sections. So I think Mac is going to be introducing the speakers, and I will be giving you, screen sharing privileges as co-host right before your talk.
Great. Great, thanks, Philip, and welcome everybody to this workshop. Really glad to see that we have strong numbers today. So we've got an awesome lineup of live speakers. We were starting here just a couple minutes late, but I think that's okay since we had scheduled a 5-minute break in, and the 5-minute break was only after the first 15 minutes of the workshop, so I don't think we really needed that 5 minutes. So let's move right on into our first speaker's talk. Our first speaker is Professor Amanda Prorock from Cambridge University in the UK. You probably are all quite familiar with Amanda's work. She specializes in multi-agent systems, multi-agent control, and she's specifically known lately for her pioneering work on applying graph neural networks to multi-agent control, which I think is super exciting. I hope she'll talk to us about that today. And some of her more traditional work in resilience and multi-agent networks, being able to design multi-agent control policies that are tolerant to faults in the communication network and attacks. Amanda, really interested to hear what you have to say. So please go ahead and take the floor.
Thank you so much, Matt, for the very kind introduction.
I get a chance to dig a little bit more into your work in the panel session.
Yeah.
Our next speaker is David Fridovich-Keil. I'm gonna actually, David, as you queue up and share your slides, I'm gonna open the audience up to ask one question for Amanda. If you have a burning question, go for it. I believe you can unmute yourselves. So just go ahead and unmute yourself. Okay, that's great. So save your questions for the panel if you have any, and we'll go right along to the next talk. So David Fridovich-Keil, he's a new professor at UT Austin. He was formerly a postdoc in my lab, and before that he was did his PhD with Claire Tomlin at UC Berkeley. He's done a lot of work in crowd robot navigation, which is quite related to this workshop. He's an expert in robust and optimal control and reachability methods, HJB, Hamilton-Jacobi-Bellman methods. And recently he's become really well known for game theoretic planning, where you have an agent who is reasoning explicitly about the interactions of multiple agents in its environment to plan its path. So David, really interested to hear your talk. Go for it.
All right, thanks so much, Mac, and very happy to be here. Thanks so much to all the organizers for having me. So my talk today is going to be a little bit of a tutorial. I'm going to try to introduce dynamic games to those who aren't familiar with them already and try to show how they can be used for multi-agent modeling. I'll show how some of the kind of modern solution methods work and talk about some extensions. Okay. So I guess to start, just let's ground ourselves by thinking about something like traffic. And of course, there's other scenarios that we can think about too, but so let's stick with traffic. So in traffic, there's lots of different vehicles, other types of road participants, but each of these participants, each agent typically has some idea, maybe implicit, but some idea of what it wants. So maybe just, I want to go forward in the lane. I want to go a certain speed. Don't want to hit anybody, that kind of thing. But these agents are all interacting with one another in the same environment. So inevitably the objectives, may conflict. And so game theory is the language that mathematically describes these conflicting objectives and what natural behavior looks like in those settings. Dynamic game theory goes a little further. It talks about games that are played over time. So think about, chess would be a very abstract example. It's a game played over time with multiple moves. So we'll try to use dynamic games as a modeling tool and a computational tool for analyzing these types of settings like traffic. Okay, so what I'll do is I'll start off by kind of more rigorously describing what's actually going on here and how do we actually solve some of these games. And then I'll actually focus a bit of the talk more on something called the information structure of games. So I'll kind of defer further discussion until a few slides from now, but this is a pretty important part of games that's kind of subtle and often forgotten about. And then I'll talk about some recent progress we've made. Okay, so dynamic games are comprised of really three main ingredients. The first one is the rules or the dynamics. So this describes there's a state of the game X at a time T. How does that state evolve in the next time step depending on what each of n players do? So U1 to UN. The second ingredient is the objective structure. So what does each player want? This, we have to be able to express this, precisely. And the last key ingredient is the information structure. And again, I'll talk about this more later, but it basically describes what does each player know when they have to make a decision. So kind of in the terminology here, if you think about player I at time T, they're applying control input or action UIT, and that should be a function of something, function gamma of something, and we have to define exactly what the something is. What do they know? Okay, there's different solution concepts in games, and there's just that they're used to model all kinds of different problems. And so the most kind of simple general type of solution concept that I'll focus on for this talk is the Nash equilibrium concept. So that's saying that we're at a Nash equilibrium if no player would like to unilaterally change their strategy. Okay. And again, to ground us back to that traffic problem, look at the figure on the right. So this is showing an intersection with two cars and a pedestrian, and basically they all want to cross the intersection at the same time. So the way we would model this as a dynamic game is we would write down the kinematics or dynamics of each vehicle. So maybe that would track things like positions, headings, speeds, and then we concatenate them all together. So that'd be the state X of the game. We could kind of imagine objectives for each player. We imagine they might care about things like staying in their lanes, avoiding each other, that kind of thing. And there'd be lots of different reasonable functional forms for that, and we'd have a design choice there. And as for information, we, again, would have many choices that, could model different, different types of scenarios, but a good sort of starting point would be something called state feedback. So say that each player gets to see the entire state of the game where everybody is at every time and base their decisions upon that information. Okay. So with that setup in mind, how do we actually go about solving these? So the first, I guess, the place to start would be to think about a game as a set of coupled optimization problems. So this is saying that each of n players is trying to minimize his or her objectives subject to the dynamic constraints, the rules of the game, over, in this case, capital T time steps. So whenever you have an optimization problem, probably one of the first things people think about would be writing down the optimality conditions, the first order conditions at least. And so the way that a lot of solvers, or the solvers that are out there for these problems, the way that they tend to work is they write down the first order conditions for every player and then just concatenate them all and throw out kind of duplicate conditions. So that's what I've done here. That's this big vector valued function G, and it's a function again of the decision variables for every player. That's the states and their inputs, and then Lagrange multipliers for the constraints. So this is a big vector valued function that should equal 0 if the first order conditions for all players are satisfied. So to actually solve for a solution to the game, we just need to find a root of all of these nonlinear equations. And so there's lots of root finding methods out there, and usually they look something like Newton's method. So that's more or less how solutions work for games these days. We can ask, what are these what is actually a root of all of these first order conditions? It's actually not precisely a Nash equilibrium. It's something called a local quasi-Nash equilibrium. So local because it's based only upon derivative information. It's not describing anything about the global structure of any of these functions. And it's a quasi-Nash. So quasi-Nash, think about it as kind of analogous to like a critical point versus a local minimum. So it's, again, only saying the function is flat. It's not saying it's bowl-shaped or something like that. So subtle differences, but good to be aware that they're there. Okay. So let me just hint at the information that this is encoding. So let's take a quick look at that. If you look at the problem that player I is solving, you can see that they're actually directly minimizing over decision variables that are states and control inputs. So like a solution to this problem will look like a set of a time index set of state vectors and a time index set of control vectors. So that's saying that player I's input at time t, UIT, will just be some constant that pops out of this minimization problem. And you can think of that constant as just a fixed function of the initial condition, x1, which defined the game in the first place. That's where did all the players start. And it's good to distinguish this from, for example, a function of the particular state that the game is at time t. So that would be a feedback control input. And this structure that we see here is actually something called an open loop control structure. So let me try to dig into this a little bit more for us. So think about feedback as when each player looks at the game ahead of them, they know that they're going to keep their eyes open. They know that they're going to get to see everything that's going on as it happens. So feedback, again, think eyes open. Open loop information, think eyes closed. Each player is looking ahead of them in time and thinking, okay, I get to see where I start, but I will never get to see anything else that happens in this game. So it's kind of like, playing a game of chess, but knowing you'll never ever get to see the board ever again. That's clearly a different proposition. You'd follow a different strategy than you would if you knew you got to see the board at every turn. So these are really different ideas of what each player knows. In some sense, they're opposites. And we'll see actually, in a more of a dynamic setting, more of a physical setting, how this manifests itself. So here's a really, I think, toy example, but it gets at what's going on. So think about an example where there's two players. I'll say player one is on the bottom, player two is on the top. And the game is going to be that player one wants player two to go to the origin, and player two just wants to get close to player one. So these are kind of coupled objectives. They depend upon each's objective depends upon the behavior of the other agents. And we'll look at, we'll start off by looking at at least to me, the intuitive solution, which is the feedback solution. So this is to say that player one knows that player two is going to get to see it all the time. And so player one realizes that if he or she drives to the origin, then player two is going to want to get close to it. So player two is going to drive towards the origin as well. And they're going to both end up near the origin, and both will be happy with that solution. So that's what you see in green. So that's really quite different from the open loop solution, which is shown in blue. And so what's going on here is, again, let's start with player one on the bottom. Player one knows that nothing it ever does will ever affect what player two sees, because player two is not going to see anything after the first time. So player one has no incentive to do anything at all, because player two is not going to see it when they have to choose what to do. So player one will just decide to apply no control input, and that ends up being a straight line in this case. Player two, on the other hand, realizes that that's what's going to happen, that nobody can see the future actions of others. So player two realizes that he can achieve relatively low cost by just approaching that straight line trajectory of player one. So that's what you see in blue. So the point here is that information structure really does crucially affect the character of what actually happens, what falls out of the game. Even though the objectives are the same, the dynamics are the same, the information being so different really does affect the solution. So let me just try to dig into this a little bit more precisely. So a feedback solution, and this is true in games, it's true in optimal control, but basically feedback essentially amounts to dynamic programming. So if you have a feedback, for example, a feedback strategy for every player, that's essentially the same as saying that you know what the optimal cost to go is from every state at every time for every player. And that's a type of object that would be computed using dynamic programming. So they're really intimately related. And if you think about dynamic programming, just about the first thing you have to do it is you have to have time separable objectives. The sort of standard thing you want to have is you want to be able to take an objective for a particular player and say, okay, well, this objective is basically the cost that I incur now at time t plus the cost I incur in the future, or some other, you may need some other function to combine them in addition. But anyway, so the typical thing is to write it as a sum over time. And if we write down what a dynamic programming looks like for this sum over time type objective, and just for player I, you get something that looks like this. And I've just decomposed it again as player I's strategy is basically to minimize his current cost, so that's GIT, and plus the optimal cost to go, the minimum over future time steps. And so what I've done is I've crucially, so this is the blue and the red boxed areas, I've added constraints to force other players to follow state feedback. And this is, these are constraints that were crucially missing in the earlier kind of open loop formulation that I showed earlier. So these constraints actually force us into a feedback solution. Let me try to, again, dig in just a little bit deeper. So the strategies here that I'm defining, these gamma IT of xt on the left, that's actually defined recursively if you look carefully. So what I'm saying is that player I's optimal strategy should depend upon the strategies of all other players in the future. If you kind of, so that's recursion. And if you kind of unfold it in your head, what you'll realize is that if there's t time steps in this game, this is going to give us t levels of nesting in the solution, or in the problem formulation here. So I guess that's good to realize, but a consequence of that is that just about any solver we might think of using for a problem like this is going to involve evaluating derivatives of these strategies. And that's just going to be a nightmare if there's so much nesting going on. So it's not even bi-level, it's so much worse than a bi-level program. Okay. So what's the way forward? The way forward is to, at least as far as we've done, is to approximate these optimal strategies by neglecting higher order derivatives. So essentially model them as affine strategies. And if you're willing to do that and kind of, I guess, follow something that looks like sequential quadratic programming, then we end up with a kind of a algorithm that looks a little bit like the block diagram on the right. So what you do is you start off with the initial strategies, some guess of initial strategies for all the players, integrate forward into a trajectory for the game, so figure out what would happen if all players followed those strategies, construct a linear quadratic approximation of the game about that trajectory, solve it to a feedback Nash equilibrium, and then update and repeat. So this is the character of the algorithm that arises when you make these approximations. This is a very efficient type of algorithm to do. It bears resemblance to sequential quadratic programming. So SQP is one of the most efficient constrained optimization tools you can use. And so this is also quite efficient. All right, I'm just gonna sort of walk us through a little bit of recent progress and then conclude, and I'd love to take any questions if there's time. So one thing that's, I guess, an important caveat of games in general, and especially dynamic games, is that there can be multiple equilibria in a game. And these equilibria can differ quite substantially. So one thing that we've worked on recently is to actually probabilistically estimate what equilibrium preferences do players have in a dynamic game, and do this in a receding horizon. Another thing is to try to design a game for robustness. And so here, what we did is we tried to design a game to model defensive driving. So this is work presented at this year's ICRA, and actually at a workshop yesterday, so if anyone was there. Another work from this year's ICRA was to account for categorical uncertainty. So this is sort of if we have a discrete set of hypotheses of what the objectives or maybe constraints of particular players in the game are. Something I should note here is that the methods to actually account for these properly require state feedback, or they require some type of feedback, and it doesn't even work for open loop formulations. So feedback is quite important here. And then the last thing I'll mention, last little vignette I'll mention is work that's was presented at a poster session earlier today and will be presented again on Fridays if anyone is interested to check it out. But this is work that we've done recently to infer the objectives of players from recent noisy data. So this is if you're trying to act in a game where you don't know the objectives of the other players in the game, you can look at the recent past and infer those objectives. So just to wrap it up, the point of the talk was that multi-agent interactions really are dynamic games. And the information structure of the game, and particularly feedback, is really, really subtle and very has very strong effects in often unintuitive ways. So what I've shown you is that we can solve dynamic games to local feedback Nash equilibria quite efficiently, and often this is in fact real time. And finally, just games are extremely flexible tools. I've shown a few little vignettes of how they can be used in other extensions that we've done. So I think there's a lot more to do, and I'm very excited to see where they go. So thank you very much. I'd love to take any questions.
All right, great. Thanks, David. Let's thank David for his talk. Cool. So we are running a little bit over, which I'd say is completely par for the course for a workshop like this. We're probably about 7 minutes over our planned schedule. That's fine. So let's take one quick question. If you have a burning question, please go for it. Feel free to unmute yourself. Be bold. Fortune favors the bold. If not, we'll have plenty of time in the panel session too. Okay. Okay, great. Yeah, in the interest of time, we will move on. So our next speaker is Saurabh Gupta. Saurabh is a professor at UIUC. And I think Saurabh really exemplifies one of the main goals of this workshop, which is bringing together perception and control in a multi-agent context for things like crowd navigation. So he is an expert in computer vision and robotics, and specifically vision-based navigation, visual navigation for robots. And he's interested in how to let vision enable robots to interact with their environments, and then also how to learn from those interactions. So Saurabh, I'm very interested to hear your talk. Please go for it. By the way, for all the speakers, I'm going to be using the directed chat to tell you your time left, just to give you cues about timing. So I'll give you a 5-minute warning, 2-minute warning, and so on. Okay, Saurabh, go ahead.
Yeah, thanks a lot for that kind introduction, and I'm very excited to be here and to be sharing some of my work. Yeah, so I'm going to talk about how we can learn to speculate about people and places for visual navigation. So again, just a little bit about me. I come from a computer vision background. So, I mean, most of my doctoral work was on computer vision, but more recently, I've started thinking about how can we apply these to building robot policies, and in particular visual navigation being one of the tasks. So my focus is going to be much closer to raw sensing, which is in the form of images that you might get from cameras and the like, right? Just to set you up. So I think efficient navigation requires us to speculate what we don't directly observe, right? And this is true for the case of static environments. So for example, I mean, this is true for static environments, particularly if the environment that you have been put in is one that you've not been in before, right? So this is, let's say, I mean, you're visiting your friend who just bought a new house or something after COVID, and now you're trying to find their couch, right? Now, you've never been in their place before, but you have been in enough other houses before that you can actually speculate that very likely you have to go around and turn right after this wall, and you might see a couch over there. Right. So this is an example of semantic regularities that exist in static environments that can allow us to efficiently navigate, right? If I did not build this speculation in, I might basically do undirected exploration, which will be wasteful and not efficient. Another example is essentially even more basic, which is even just figuring out the spatial traversability in an environment, right? So this is, for example, a hotel room, and you are trying to get out of this bathroom. And again, you may not have been in this specific bathroom, but you've been in enough hotel rooms that you know that if you were to go out and turn left, there is very likely going to be free space and you can exit the room from over there, right? So this is, some examples of semantic regularities in static environments, which require us to speculate what we are not directly seeing. I think the same is actually true when we are talking about people in dynamic environments. We have to speculate what they are going to do. And doing so is actually critical for basically navigating effectively in cloud and so forth, and as many people have talked about. Now, I think I'll make a distinction here. So I think what David presented in the talk right before me, he's saying that we should model these as games, right? And I think that makes a lot of sense. But I think there is also a perception component over there where, this is actually the feedback that David was talking about, which is you need to react to how people are reacting to what you're doing and the like. And for that, we will need to build perception models, and how to do that, I believe, is an open question, right, in some sense. So I think today I'd like to give you a flavor of how we can do this. I'll talk about some of my past work where we do this with static environments. And I'll give you a toy example of our very first attempt of doing it with people, which actually doesn't look real at all. And I'll just present it just for the sake of, first step at the problem. Right? Okay, so let's get started. Right. So I think the general form of how speculating about places looks like is of the following form. Right. We have an image that we have been given. What we are going to try to do is to learn a function f, which takes this image and tries to make speculations, right? And this speculation could be in the form of nearness to goal, right? So this is actually very, very direct. I'm basically trying to learn a function in which direction, going a certain distance, let's say 2 meters, will I be closer to a couch than the current location, right? So I can set it up in this fashion, and I can now, question is how do we learn this and so forth, but believe me, we can do that. And let's say you do that, now you basically have this function which can predict, let's say it can make this prediction that this is, these are promising directions for exploration. Now, once you have this, you can actually pursue the direction which has the highest score, and you can build a map, topological map, metric map, whatever you have, to keep track of where you have been, where you've not been. And this is one way in which you can incorporate speculating your speculations about where to go in a navigation policy. You can actually do another thing, which is that you can take this image that you've been given and you can try to predict implicit or an explicit top-down semantic map, right? And this could be explicit in the form you can represent object categories that you're seeing. This could be implicit in the form that it's just some feature vectors for locations around yourself that you're just storing around. And now once you have these, you can actually learn another function G, which takes in this semantic representation of the space around you, and it tries to predict the action that the robot should take, right? And now again, right, and again, through this process, you can learn about how to speculate about where you are, right? Now, there are design choices that are involved over here, which is what is the form of the function f and g, and how do you train them, right? And again, there are lots of different choices. You can use transformers, you can do CNNs, you can use classical methods for representing f. Similarly, for G, you have lots of options. You can use a classical path planner. You can, in fact, learn a planner and the like, right? So there are all of these varieties, right? Now, I won't present all possible things. I'll maybe present actually the earliest of these. And I think, I won't say that this would basically be the, I think this is more just to get the point across that we are trying to do these things with learning. There's obviously more things you can do to simplify training and all of that, which I won't get quite go into. Right. So here, the basic setup is we've been given an image from the first-person camera of the robot, and we have a goal that we want this robot to go to. Now, what we're going to be doing is we're going to be building neural network-based policies, which essentially build a spatial representation of this world. It uses a mapper module to produce this representation, and then it uses a planner module to basically, which takes in the spatial representation along with the goal specification to output the actions that the robot should execute. Now this repeats over and over again. You get the next image, you get some ego motion. Again, this goes to the mapper, you update your map, you basically, again, hit it with a planner, get an action to execute and so forth, right? So this is basically standard what you would learn in a robotics class, which is you build a map, you do path planning on top of that. But the interesting thing over here ends up being that you can design, you can make choices for F and G, which make this entire pipeline differentiable. And what that allows us to do is to essentially learn the representation that we are building of the space for the end task that we're interested in, right? So in this particular case, instead of being limited to building a spatial representation of the world in terms of occupancy of nearby space and so forth, what we can instead do is we can learn abstract representations of the space around me, right? I mean, I'll just say a little bit about what these spatial representations are. So in some sense, what we are building is we are interested in ground navigation robots. So this is, you can think of this as a top-down map. We are building a representation for what you are seeing around you, as well as how confident are you about what you are seeing. And you have to make a choice of a coordinate frame. The coordinate frame that we chose in this particular work was an egocentric bird's eye coordinate frame, where the agent is always at the center looking upwards. And in some sense, what this representation is essentially doing is that for this particular location, this is, let's say, somewhat in front and to the right of the agent, we are storing a feature vector which essentially corresponds to what the agent thinks is over there, right? So that's kind of what that is, right? Now, I will not go into numerical results and how do you train this and all of that, but I'd like to give you some visualizations to make a point, right? So here is an example of this. So we have trained this agent. And now what we're going to do is we are going to take the representation that the agent is building over time, and we'll try to see whether this representation can actually make predictions for quantities that we might think should be important for navigation, right? So in particular, what I'm showing on over here is essentially a property that we are predicting, which is free space, right? So if this is a robot that is navigating, it better build some representation of free space, right? And again, the coordinate frame is the same. Agent is at the center looking upwards. And this is the first image that you're seeing in this particular sequence. And the agent has never been in this particular environment before. And clearly there is a wall and that's obstructing part of the view, but the agent is actually able to represent, build representations which can be decoded to free space, even though the agent has not explicitly seen free space just yet, right? Now let's actually play this video a little bit further. So this agent walks out of this particular room. And now once it has actually seen the freeway, the hallway, then of course the predictions for freeway become much stronger. We run this video a little bit further. What you see is essentially at this particular location, it's only seeing the door. It's not seeing quite a lot inside the room, but it can still make a prediction that there is very likely going to be free space on the left inside this room, right? I mean, you can take this further. You can actually try to decode whether it is only able to represent free space or can also represent other semantic representations, right? In this particular case, whether you're inside a hallway or whether you're inside the room, right? So this is another, I mean, it's the same thing. We are hot values over here are essentially hallways, and over here are rooms. And again, right now this agent is in a hallway, and then once it enters into a room, then the prediction for it being inside a room lights up, right? Now, again, I will emphasize, none of this was explicitly supervised for the agent. The agent is learning this purely for the task of finding objects and environments. And these are emergent representations that happen to emerge over the course of training, right? So that's kind of what's happening over here. Now, I think, right, so, and again, we can actually do this. I mean, you can see the emergence of some kind of semantics that when we train these agents for finding chairs, the typical behavior you will observe is these agents will try to go inside rooms because rooms are typically full of chairs. And that's a good prior policy to act via in order to get to objects of interest, right? Okay, so I think this is kind of what we started with. And recently we've been thinking if we can extend the same ideas to speculate about what people will do and build models on top of that. And this is more recent work. This was done in collaboration with folks at CMU, and this was presented at ICLEAR last year. And the story here is actually fairly similar. Here we are going to basically be building affordance predictions, right? So we have an image, and again, let me qualify this. Earlier work was done in real environments, like scans of real environments. We also did some real world testing. This particular piece, because it's just so hard to train with real people and everything. I mean, we are doing this in actually Doom, which is a video game. And again, I will not call this that we are doing social navigation. This is basically learning to play the game of Doom slightly better, if you will, right? But I think it still uses the same principles, and so I want to talk about it. Right? So what we are essentially doing is we are again learning a function f, but in this case, we are learning a per pixel prediction function. So for each pixel, we are essentially trying to estimate whether this is an obstacle or this is not an obstacle. So what we are doing is you can think of it as a semantic segmentation network, which takes in the first person view image and produces a first person view output, which is essentially a binary vector, like a scalar per location about whether there's an obstacle over here or not. Now, how do we train this? This is essentially trained. The way we use this dynamic obstacle map is by essentially gating the occupancy map that you get by using a depth image such that navigation succeeds, right? So on the bottom, we are assuming you also have a depth sensor. And now using this depth sensor, you can make this top-down traversability map. Now this top-down traversability map will only represent this agent in the location where this agent is right now. But what we want to keep track of, where can this agent that we are seeing go around in space, right? That's kind of what we want to speculate. And the way, therefore, that we do this is essentially by gating. That's kind of the role of this dynamic obstacle map, where we basically take this dynamic obstacle map, we use this to we take points that have been mapped over here as being obstacles, and we now project them into this depth map and basically mask out the traversability wherever obstacle points are being projected, right? So this dynamic obstacle map allows us to change geometric traversable maps into something that is actually cognizant of the dynamic behavior of the agents that we are seeing in there, right? And now this can again go into a path planner, and this will output actions that you can execute. And again, how do we train this? Again, this is a video game. I do not recommend training this way in the real world. Actually, maybe that won't be that bad. But anyway, the way we are training this over here is we sample a point, we try to go over there. These agents have some behavior that they exhibit, which is that if you come close to you, if you come close to them, they will attack you and kill you, right? So in this case, supervision is coming very explicitly in the form that you will die and you don't want to do that. But we use this to basically generate labels of this form that, if you end up in this region, you will die. If you end up in this region, you're fine, right? So this is where we are getting supervision from. And again, if you do this, it turns out you can learn better policies. So green is essentially a policy for exploration, which doesn't build any kind of speculative notion of dynamic obstacle of dynamic agents in the environment. Orange is the line where we are doing that, and we see a little bit of improvement. Here's another plot which shows how sample efficient or inefficient this process is. So this is how many frames do we need to label by walking into monsters and getting killed. And I'm not very proud of the sample complexity here, but I think this is just a proof of concept in some sense. Here are some visualizations. I guess I have 1 minute. I'll try to wrap up. Here are some visualizations, and if you notice, I mean, here there are basically obstacles which are static. These are some whatever chests of something, and you see that the obstacle prediction is localized to exactly being on these obstacles. But whereas if you look at this agent, I apologize for the low contrast on these images. If you look at this, what you will see is that it basically looks at this person, but then it smears this kind of that there is an obstacle quite kind of all around this, and this kind of reflects into the map that we are building and so forth, right? Okay, I think that's kind of all what I wanted to talk about. I will leave with 2 points of discussion. And the first one is, again, going back to the fact that we are learning these in some sort of a end-to-end fashion, if you will. And the question I want to pose is, do we need to explicitly map and forecast trajectories, or can we take some sort of a shortcut of the form that I presented over here, right? Now, I'll admit the shortcut that I presented, I mean, I don't know if I can do this in the real world, which brings me to the second point, which is there a way that we can, I mean, if you believe in the first point, then is there a way to train such policies in the real world? And for people, I don't have any results, but for places, I think we have quite strong results. I'll encourage you to look at these more recent papers where we have worked out how we can train these speculative policies that speculate about places through for example, use of videos or through use of supervised learning, which is not as sample efficient, is not as sample, it has much better sample complexity than what you would. And with that, I'd like to end, and I'm happy to take questions and discuss further during panel discussion as well. Thank you for your attention.
Perfect. Thank you, Saurabh. And thank you very much for staying on time as well. Let's give Saurabh a hand. All right. Any burning questions? One or two? Really, be bold. Just unmute yourself and go for it.
Hi, I had a quick question regarding, I guess, the Doom example. I was wondering if this is already has been learned, or it's some perhaps future work. Let's say that these enemies move between two objects that you can recognize semantically, like between a refrigerator and a stove, right? Would this method learn to perhaps stay away from the, I guess, shortest path between the refrigerator and the stove? Does that question make sense?
Absolutely, the question makes sense, and I mean, so in this case, we didn't have. So the semantics of the agent in our case was the agent comes towards you if you come within some region of it, right? It's very simple, which is like essentially it's like some space around the agent is non-traversable. But if this agent had a particular way in which this agent was moving, then I would imagine that with enough training, we would have learned that, okay, don't go along this path, right? I think that would have gotten learned, because if you were in that path and the agent ended up being there, then you would die, and then that would say that that's non-traversable, and then you would be able to learn that. And again, we are using neural networks, so presumably the same behavior in some other environment could also be recognized in the same way, right? But again, we have not quite done those things. So I won't make claims about that just yet. But,
right. Yeah, it would be interesting to see if you could learn such a behavior with more complex enemies.
Absolutely, yeah, I agree, completely agree.
Thank you.
Thanks.
All right, great. Thanks, Saurabh, and thanks for the question. So our next speaker is an unexpected but very welcome surprise. So the speaker is Rohan Chandra, who's a PhD student near finishing his PhD in Dinesh Minocha's group at University of Maryland. Dinesh unfortunately wasn't able to join us today, but Rohan does some really fascinating work in multi-agent driving, where he's looking at methods and metrics for predicting aggressiveness or certain simple to distill behavioral metrics on the behaviors of other cars in the local vicinity of an ego vehicle. So Rohan, please go ahead and take it away.
Thanks, Mac. Thanks for the kind introduction, and I thank the organizers for having me and accommodating me at this last moment. So, okay, so hi, I'm Rohan, and today I'll be talking about human driver behavior modeling in dense urban traffic with applications to planning and navigation. So, a little bit about myself. I'm a fourth-year PhD student in computer science working with Dinesh Minocha at UMD. Some of my short-term research goals are to develop algorithms and systems for autonomous vehicles for planning and decision-making with humans in the loop. And some of my longer-term goals are to generalize human-in-the-loop planning and decision-making to multi-agent systems using algorithmic game theory. And another long-term goal that I have is to help autonomous vehicles drive in India. And this is a bit tongue-in-cheek because it's a very, very lofty goal, and it's not clear whether it's realizable or not. But thinking about that problem statement and just trying to figure out ways in order to achieve that has been sort of the main driving factor and the motivation factor for a lot of the work in our lab over the past few years. So before we get to the main topic of behavior modeling, I want to be really clear about why we would want to model driver behavior in the first place. And in order to do that, I want to compare traffic in the US versus traffic in more East Asian or Eastern countries like India. So if you say, I'll let you watch the movies for a few seconds. So if you see these traffics, a few things immediately jump to mind. And some of these things may be obvious, some of these things may not be so obvious. But some of the obvious things are that in traffic in places like India, there are no lanes, there are no rules, and it is more of sort of freestyle driving. And a little bit of correction. When I say no lanes, there are lanes. It's just that they are more for decoration than for actual lane following. So the obvious question now comes up when there are these kinds of structures in place, or lack of structure, like no lanes, no rules, more freestyle driving. So what are some of the things that we need to learn from this? So what are some of the key takeaway messages? Well, first, traditional deep learning based perception will fail almost automatically and immediately. And they could be due to a variety of reasons, which could be occlusion, it could be domain shift because of the heterogeneity, because of the traffic density, and it could be due to a variety of reasons. And the second takeaway message is that the planning methods will also fail. And that is primarily because there is no planning algorithm in existence that can handle this kind of dynamic environment. And it's also partly due to the reasons I mentioned before, which is no lanes, no rules, and more freestyle driving. And so this sort of begs the question, how do people in India therefore drive if, if there are these kinds of problems? And the answer to this question is actually very interesting. And it turns out that every driver in India at every instant of time is solving this problem of behavior modeling or behavior prediction. And what I mean by that is at every time instant, every driver at a subconscious level is watching the movement of all the cars around him and sort of guessing the way they are going to move. And it's interesting and very coincidental, because the ideas that David and Amanda spoke of in their talks before me, it's sort of a manifestation that is happening here at a more subconscious level. That is, drivers are communicating with one another, and drivers are sort of performing some game theoretic formulation with one another. And they're solving this problem of behavior modeling at a subconscious level. And that is sort of the intuition and inspiration that I'm taking from the driving patterns in India. And my problem statement is to predict the behavior of the driver given only the trajectory of the vehicle and nothing else. So I want to predict how aggressive the driver is, and aggressiveness can fall on a scale. So there's no discrete, it's not a discrete label, it's a continuous variable, and it falls on a scale from very conservative to very aggressive. So there's some prior work that is in this field, and the most notable one is the social value orientation, which determines the selfishness or the altruistic nature of a driver. And it does so by optimizing an objective function using inverse reinforcement learning. Our work, or our driver behavior modeling, is very similar in a lot of ways, in that it tries to achieve the same goals. It tries to model the behavior of the drivers using trajectory features. It also differs in some ways, but in the interest of time, I'll leave that for discussion later. But I just wanted to point out some of the prior work in this area. Right. So now coming to my main approach of modeling driver behavior, it rests on this notion of relative behavior. And it's going to tie up to what I was talking about, what happens in Indian traffic. I want to best demonstrate this to a couple of examples. So let's say a vehicle drives at around 65 miles an hour, and we want to determine whether it is aggressive or conservative. And this is all the information that you have. And you can see that happening, because if you only have like a camera or LiDAR sensors on the vehicle, then this is only the kind of information that you're going to get. You're only going to get the positions, you're only going to get the velocities. So if you have 65 miles per hour, the answer depends, because it can be aggressive in a city, but neutral on a highway, right? And a similar question arises that if a vehicle changes lanes 3 times per minute, is it aggressive or conservative? Again, so this could be aggressive for a truck, primarily because of its mass or volume, but maybe not for a car. And again, like this is again very subjective, because we don't even know if 3 lane changes a minute is high or low. Who decides these thresholds? And it also depends on the traffic density. So The whole point is that given the information that you're obtaining through commodity sensors on a car or on an autonomous vehicle, which is like a radar, lidar, or camera, you can't really, you don't really have the enough information to predict something which is as subjective as aggressiveness. So the main intuition or inspiration is that humans observe driver behavior relative to themselves. And that is exactly what we do if you think about it. We don't, we don't prepare questionnaires for the drivers in front of us. We actually just observe their movement or the trajectory of the vehicle, and we sort of compare it with ourselves, and we make a sort of judgment as to whether they are aggressive or not. And that idea is modeled using a graph theoretic concept called vertex centrality. So in vertex centrality, every vertex can model the relative behavior in a neighborhood with other vertices. And essentially, the vertex centrality is a real valued function that describes the importance of a vertex with respect to its connected neighbors. This is very high level, and I'll just link the paper in a minute, and more information can be found there. But at a very high level, what I'm doing is I'm forming a graph over the traffic snapshot, right, where the nodes are the traffic participants and the edges are the intervehicular distances between the agents. And I use this graph theoretic concept called vertex centrality to measure the behavior. Now, just a bit of background for vertex centrality. So vertex centrality has been used in many different areas of computing. Google's PageRank uses it. The chess uses it to rank chess players. We can use it to determine locations of pandemics, and it's been used to model coronavirus hotspots. We can use it to identify addresses of computers on the internet. So these are all places where vertex centrality has been used in graph-based applications, and I'm using this in traffic now. So there are many different kinds of vertex centrality functions which essentially measure different kinds of graph properties. I will sort of just at a very high level go over two of them. The degree centrality measures the number of edge connections to a vertex. So it's essentially counting the number of outgoing or ingoing edges. And the closeness centrality, it solves the single source shortest path problem for any vertex. And this sort of measures how central the vertex is in a graph. And you can sort of see the intuition behind this, right? So if a vertex is kind of like in the middle of the graph, the shortest path to every other vertex will be sort of different from when the vertex is at the edge of the graph. And why these two, I bring it up, or I define these, or I use these two functions, is because we can use these centrality function definitions, not as is, but you modify them in a way, and you can use a degree centrality to model longitudinal indicators like overspeeding or slowing down, longitudinal as in along the axis of the road. And you can use the closeness centrality to model lateral behaviors like perpendicular to the axis of the road, which is overtaking, sudden lane changes, and weaving. And by combining these centrality values in certain ways, you can actually figure out the degree, intensity, or the likelihood to which an agent will perform these longitudinal or lateral behaviors. So this is sort of like the core technical contribution of our work. So now let me just walk you through like a toy example on how the closest centrality can model a lane changing vehicle. So now, essentially, I take a traffic snapshot, okay, at t is equals to 0, and the same traffic at t is equals to 2 on the right. Now, this is like a very toy graph of a traffic, but I want to focus on this agent 1. Yeah, so agent 1 is the ego vehicle in red, and as you can see, it goes from the edge of the graph to the center. So this is sort of simulating a lane change in Python. And these green vehicles are its neighbors, right? So now what I do is if I can just take the closeness centrality and I can measure it at when it was towards the edge versus when it was towards the center. And the closest centrality changes. It goes from low to high value. And this is sort of like a very, very, the nuts and bolts of the algorithm. And then you can use this to model the behavior. And I'll show some results based on this in a bit. So our approach in a nutshell is that we take the input trajectories by reading in the coordinates of every vehicle at every time frame. This can be, absolute coordinates in GPS form, or it could be relative to ego vehicle. We form the traffic graph where the nodes are the vehicles and the edges are the distances. And then we use centrality functions to compute the closeness and degree centrality. This is a very high level and it's all explained in the paper. So in interest of time, I'll just play a quick video demonstrating the results. So now here I'm modeling overspeeding. The green vehicle is the ego vehicle. The blue are the surrounding vehicles. The green vehicle is going to overspeed. And what I want you to notice is that the degree centrality will monotonically increase as opposed to the blue vehicles where the centrality will be flat. So next I'm going to show a lane change. So the green vehicle right now is in the second from the top lane. It's going to change lanes to the bottom lane. And the closest centrality behavior, it changes the behavior by going from top to bottom. And we have some real world results as well. I'll just speed through them because we're running low on time. So this is an instance from the Argoverse dataset. So these are data sets collected from Argoverse and a private data set collected in Singapore, where we show vehicles either overspeeding or they're either performing lateral maneuvers. And we use the closures and degree centrality to model those behaviors. So a few benefits. Our method is robust to noise and perception. And why I thought this is worth mentioning is because we found that we can perform or use our approach without any data processing or data cleaning or data wrangling, and it just works in a very plug and play format. So all you need is like a text file with trajectories of the vehicle and positions of the vehicle, and we can actually estimate or predict or model the aggressive behavior or conservative behavior with 100% accuracy. It's generalizable to many traffic environments. With minimal to no assumptions. And we tested in traffic in US, India, China, and Singapore. So very briefly, just as I want to wrap up, I want to talk about like one application. So we took this behavior model and we used it for behavior guided navigation using reinforcement learning. This is a separate project on its own, and I'll just reserve one slide for this. And I want to show this one result where we got. So I'm not sure if you can see. So in the top row, what is happening is the green ego vehicle recognizes that the red is aggressive. So here red are aggressive and blue is conservative. So the green agent, ego agent, recognizes that the red is aggressive. It slows down, allows the red to pull up ahead or go forward, and then it again starts speeding up, right? That's what's happening in A, B, and C. In D, E, F, what is happening is the opposite. So it's interacting with the blue conservative agent. It recognizes it as conservative and it confidently overtakes it. So what's happening here is that in a simulator, when we have aggressive and conservative agents, we're teaching an ego vehicle to recognize which agents are conservative, which agents are conservative, and we're actually teaching it to behave accordingly in those specific circumstances. So it will behave carefully in aggressive interactions. It will behave confidently in conservative interactions. And one consequence of doing so is that we measure the collision frequency of a behavior-rich policy in orange versus the default policy, which is not behavior, in blue. And we show that the collision frequency actually decreases by a considerable margin when we apply behavior-rich policies. And this is a very dense scenario comprising of 40 vehicles. I essentially want to conclude by saying that behavior modeling in autonomous driving is going to be essential as we master driving in simple scenarios like developed countries, and we want to move more towards developing countries, or we want to move towards dense urban traffic. We need to do behavior modeling, and by behavior modeling, it's not just trajectory planning. We need to sort of make a guess on whether the driver is going to be aggressive or conservative. We show that vertex centrality as a graph theoretic concept can model aggressive and conservative behavior. And we also show that behavior modeling can improve downstream tasks like multi-agent navigation. Thank you for listening to me, and I can happy to take questions.
Great, thank you, Rohan. Let's thank the speaker. All right. So one quick question. Go ahead and fire away if you have a question for Rohan. Otherwise, we can save it for the panel. Okay, great. So we'll save our questions for the panel and we'll move on to our last live speaker. Last but definitely not least, I am pleased to introduce Adrien Gaidon, who's the head of ML research at Toyota Research Institute. So Adrien comes from the machine learning and perception world. And Adrien and I have been working together on a thread of research aimed at trying to understand and bridge the gap between perception and control, or perception planning. And I believe this is going to be the topic of his talk. So very interested to hear what you have to say, Adrien. Obviously, it's highly relevant to the topic of the workshop. So Adrien, please go ahead and take the floor.
Thanks, Mac, and thanks, Nagar and Philip, for inviting me. It's a pleasure to be here. And exactly, yeah, the title of my talk is going to be about how to bridge the perception control gap with prediction. I think everybody can see my slides well. All right, then off we go. So first of all, we do a lot of different research at TRI. So we do, especially I come from a machine learning computer vision background. So we do in the team, we do a lot of scene understanding, self-supervised learning, in particular for 3D vision. Also use simulation a lot, auto-labeling. And recently we've been doing more and more prediction, behavior modeling, learning for planning and control, and trying to connect the two. Because very often it's, you know, in companies, it's treated as separate teams and it's treated as separate modules and everything is separate. And when you put it together into a single robot, magic happens or not. and so I think what really I was really interested in this workshop and collaborations with Mac and others to really start to look at the interfaces. All right. And the reason why it's really important to look at these interfaces and take a step back and a little bit look more broadly at the problems is because a robot is a complex sensory motor loop, which is starting to dawn on people. Because in autonomous driving, a lot of people have promised things a lot for many years, and now we're in 2021, believe it or not, and you cannot drive, you cannot have a self-flying car or these kind of crazy things. So reality hits you in the face. So autonomous driving is hard. Now the question is why? Why was it maybe underestimated, and why is it hard, and why do we do research at Toyota on these topics? You can listen to Niels Bohr, for instance, who, I mean, it's a famous Danish proverb which is attributed to Niels Bohr, which is prediction is hard, especially about the future. And this is the crux of it. I think if you look at it again, like a robot, any robot is a complex sensory motor loop. And that's where, like, you know, it's different from AI at big tech companies, which is just disembodied. Here we're talking about embodied physical systems that are safety critical very often. To have data, perception, prediction, planning, and control. And in particular, the emphasis of my talk and where I think a lot of the research is starting to pour into is the prediction component, which is not by accident in the middle of this chain. And it's difficult because humans, right? So the first question is, well, okay, if it's difficult, do we even need it? Can we just skip that? Like, you know, go back to the previous diagram, have a skip connection, like shortcut, no prediction. And that's an interesting question to think about, right? When you say prediction is super important, okay, do we actually need it? First of all, humans are really good at taking risks. Like, why is that an interesting question to think about? There's a lot of tragic deaths, right? And this is the motivation for why we're studying that problem. It's so important societally, like autonomous driving, safety systems, etc. But these deaths are over lots of miles. So in the US alone, it's basically one fatality every 100 million miles. So it's very, very hard to beat humans at this scale, right? And this is the objective. This is what we want to do. So, so first getting there, we're very far from it. So it seems like imitation learning might be like a principled approach to first be able to even approach human performance. And we can collect a lot of good demonstrations. So machine learning and imitation learning in particular seems to be very well placed to tackle this problem. So to the extreme, maybe imitation learning is all you need. It's simple, it's scalable, it's end-to-end trained directly for the task of driving, if you define it as imitation. Throw all these boxes out that I talked about before and just have a big neural network. Well, we and others have tried that. But sadly, as you can expect, and as most people in robotics knew before, and it's naive, right? It's naive, and because you need the structure from the problem. What are the problems that arise when you throw away the structure? Get bigger models, pre-training, more data helps. We use ResNet. We did a lot of the tricks in the deep learning world, which is where I come from. And what you have is issues that now machine learning is recognizing in the real world, which is data set biases, variance issues, right? Even though it's pure regression, depending on the shuffling order that you see your demonstrations from, because we always assume everything is IID in machine learning, you might get very different models in return. And you have also more deep problems that are the root of the lack of structure, which is causal confusion, for instance. So I think probably most of you didn't need convincing, but some people in machine learning did need convincing. There is no shortcut or skip connections, right? As it's in machine learning. It just does not work. And anyway, that is not what we want, right? That's not what the end customers would want or the society wants, because we want autonomous agents that can reason, explain, provide safety insurances. And this is why intermediate representations of the past, the present, and the future are required for safe human-robot interaction. So you have to solve the prediction problem. Okay, we have to solve it. But now, why is it hard? Is it really that hard? So first of all, in multi-agent human-robot interactions, you have to deal with other autonomous agents. I know it's surprising, right? Like in many demos you see in robotics, it's like a robot by itself or with other robots. But in the real world, why it's hard is because robots and humans will have to interact, potentially at high deadly speeds. And so the problem with humans is that they're autonomous agents. So they have their own intent. And that intent governs their behavior, I will go and leave through that path because I want to go and have lunch, for instance. So there's something that governs their behavior, but we don't have access to it, right? Directly, at least. We cannot read into the mind of the people. So instead, we have to infer it from interaction patterns and contextual information, right? As like people tend to behave in certain ways. There are certain things in the environment that is indicative of what people might want to do. And so this is why we can basically be able to tackle this task in the first place. And so we've been together with colleagues at Stanford, we published a paper and a data set for pedestrian crossing prediction, because that's one clear application of predicting the intent of pedestrians, and where we used graph neural networks to predict pedestrian behavior from spatiotemporal scene graphs, such as those that you get produced by standard perception systems, like the ones we have in our cars, right? You parse the scene, and then you have a graph of entities in the scene, and you can link them through time, and then you can basically reason about their interactions. And graph neural networks are a really good tool for that, and including recurrent models. And one of the cool benefits actually of this work, and I apologize for being very of a teaser nature talk, because I'm going to skip over a lot of details just to go and stay on time. You can switch it, basically the switch you can say, instead of is that pedestrian going to cross or not, you can switch it to is a pedestrian going to cross in front of me at some point. And that enables like some scalability benefits and things like that. So prediction is hard because of intent, that's latent. It's also hard because of multimodality. And that comes from contingency. So there's many plausible futures, and many things could happen, many things people would want to do, and so we have to always predict a distribution over plausible futures. And how do we do that? And again, because we're talking human-robot interactions, one way is to structure prediction in the same way as humans make decisions. This is a work we've done also last year together with Berkeley on trajectory forecasting of pedestrians. And the idea, again, is using the human decision-making process. So we decompose it, and first by saying, what are the intents, potential latent intents of the end user? So we predict, here in this case, we basically just equate intent with destination, for which we have the information, again, like historically, right? We assume that where they went is where they wanted to go over a sufficiently long horizon. And so we first learn a distribution of plausible destinations, our intent, condition trajectory forecasting on the sampled endpoints, and then plan following social norms, which is where people might move in ways that they don't really intended, but they have to, physics or whatever. So multimodality was the second thing, the second reason why prediction is hard. Uncertainty is the one where I want to spend most of the time of the rest of the talk, and because that's the big one. One of my former mentors is Wolfram Burgart, and co-wrote the book on probabilistic robotics, and that's something that he really taught me, is that basically every state is a distribution. And what we're doing, because we're dealing with the real world is stochastic, some would say chaotic. So every state is a distribution, and that's a principle to embrace. And that is actually a problem in practice, and why sometimes people try to ignore that fact and avoid it, because we deal with, again, a complex sensory motor modular system. So there's many different modules that are involved to make a robot work, and uncertainty must propagate throughout. And this is hard. And so that's why even in the spectrum of uncertainty work, most people focus on predicting uncertainty, saying, oh, my model will output some form of uncertainty, maybe consume some form of uncertainty, and then other people will figure out what to do with whatever I produce as uncertainty. And as I mentioned in the previous works, that was a big focus of the work, like predicting multimodal distributions of potential future trajectories of agents. But one of the things that I think is really needs much more attention, is understudied, is using this uncertainty. Really, we have some mathematical tooling to produce that uncertainty, but using it, sometimes the math is not there, or sometimes it's not really clear how to really represent even the uncertainty. And I mean both upstream and downstream. So again, upstream and downstream is relative to prediction. If you go like data, perception, prediction, planning, control. So let me talk a little bit about some of the research we've done. As I mentioned, with all these, and we'll start basically with the downstream usage, because that's more of the work that we've done recently, including with collaboration with Mac and Negar, and other folks at Stanford, like Marco Pavoni. So with all these efforts on probabilistic prediction, there's so much work producing probabilistic prediction outputs. How do we actually leverage prediction uncertainty in planning and control? And this is a big part of the perception control gap, I think. And it requires special interactions between prediction and planning modules, which are, I think, not solved exactly how to architect that. So we recently worked on this topic with Stanford, as I mentioned, by leveraging in particular the framework of risk-sensitive stochastic optimal control, which Max Lab is really knowledgeable and pushing the edge on. And one of the main novelty of our work is relying on this notion of entropic risk. And the entropic risk measure, which I think is also known as exponential disutility, and I think more the economics and control literature, is like old, it's like 1970s. But it's been really kind of brought to the modern age of like deep learning and robotic stacks, I think, with the works we've done with Mac and co. And what's nice is that this risk measure it's very simple. It applies the exponential transformer, sorry, too much computer vision. The exponential transformation to the objective J with a user specified scalar parameter sigma. And if you Taylor extend this risk measure, you can show that it approximately decouples the mean and the variance of the objective when sigma is small. And that really shows that, oh, now we're talking about risk in terms of like this variance term that's captured directly in this entropic risk measure. So from this, actually, you also can tell that this risk sensitivity parameter, sigma, it determines how much we care about the variability, right, of the stochastic objective, in addition to just the mean. You don't want to do just well on average. Larger sigma value increases the risk sensitivity, and risk neutral is recovered when you set it to 0. So I won't go too much into the details, but at a high level, we propose a framework called RSSAC for risk-sensitive stochastic sequential action control, which was led by Haruki Nishimura. And it enables safe crowd-robot interaction via this use of this risk-sensitive objective. And one of the things I mentioned again is like plugging in prediction with planning. So really the core novelty of this work was really a lot of this interfacing work, right? And how do we use explicit probabilistic prediction of human motion in this risk-sensitive based planning and control. Note that also like there's one paper also that we've done actually with Mac and Negar, led by Mingyu Wang, and where we're looking also at the same ideas of game theoretics, so stuff that was talked about earlier. And when you have multiple agents that are risk aware and they need to interact. And finally, so that's like some example of RSAC in action, and you see like all these trajectories all over the place, and the agent in blue that needs to basically consume all that information, that's uncertainty, and be able to plan safely. And recently we've done some work again with Haruki and Mac on distributionally robust control to extend these to model misspecification and things like that. So another way to also see the problem is to flip it on its head again. And instead of modifying downstream planning and control algorithms to use common representations of uncertainty from standard trajectory forecasting methods, instead we can modify prediction to output what planning and control needs, right? Versus saying planning control, here are a bunch of trajectories, deal with it. And so here in particular in planning and control side, we recently reasoned in terms of dynamics. And so can we have prediction reason also in terms of dynamics and output things, data structures that are compatible directly? And we studied this direction in a paper called MATS, which was led by Boris Ivanovic and Marco Pavone's lab. And where we learned to predict a mixture of affine time-varying dynamical systems. And here what's important to note is that the state SZ corresponds to the concatenated state of all the agents in the scene. And we're predicting the dynamics of all of the scene, basically. It's indexed by Z, and that's because the multimodal uncertainty of this representation comes from a high-level latent variable, which is used to represent like different categories of scene-level behaviors. In traditional way, it's done in prediction with a conditional VAE. One of the benefits also of this approach is not just that, oh, it's easier to integrate, but it's also interpretable. Again, it's like written in a clear form, decomposed in the way you see. It's more amenable to downstream planning, and that's the goal, and control algorithms like MPC in particular. And we use a variant of contingency MPC in the paper. And so because it's easier to integrate, it's more efficient than tracklet-based predictions too, which is also very important to be able to do real-time inference. Has other benefits, but I'll skip over it. And last work that I wanted to talk about is I mentioned again, like we need to use uncertainty upstream and downstream. I started with downstream because there was a lot of the work of like how to integrate it with planner, because there's a lot of research on prediction already. But what we found is that if you go up a little bit, up the stream a little bit, then you realize that there's a big problem with prediction today, which is it assumes perception is perfect. The state space that the inputs that prediction algorithms consume is like output from perception, but it's idealized. And so I think that's just very dangerous and very wrong. And that might not be seen so much in like cleaned up data set where everything is nice and cleaned, or even in certain field tests where everything is like very close to the domain of training and everything. But we know that actually perception system and deep learning systems are not perfect. So in order to be, and probably will never will, right? And I work on them, so I'm fine with saying that. But in order to be robust to the real world, they need to accept not erroneous tracks, but like distributions over percepts. And so again, with colleagues at Stanford, we studied this problem in a paper called Haiku for heterogeneous agent trajectory forecasting, incorporating class uncertainty. I think I'm running out of time, so I'll just be brief. But first of all, as I mentioned, nobody really studied that question before because they were all living in Disneyland of like perception is perfect, and the data sets were Disneyland data sets. And so we made a data set from TRI data, historical logs, where we mined hard scenes where perception actually flickers, has challenges due to the long tail, and where we actually have also saved all that perceptual uncertainty information produced by the perception components. And so we will release that data set this year. And then the second thing is, okay, now we have this data set where we can study this question. And so what we did is we took an existing state-of-the-art approach called Trajectron++, again, done by our Stanford colleagues. But this time, so this is how it looks like. So you have multiple LSTMs that encode the different agents. You have one encoder per agent category. So again, here you're basically saying, I know that it's a car, and then I use the car LSTM to encode the car trajectory. But what if it was not a car? What if it was a truck? What if it was a motorbike? That is gone. You've made that mistake, and you're basically just going to pile on. So instead, we can do some extensions at different parts of the model, more specifically on the encoder, to basically augment this with the full distribution over the state and have a single encoder that is shared basically across all agent categories, because now instead it's just a trajectory encoder conditioned by the semantic uncertainty. And the benefits are that it corrects a known problem in deep learning, which is being overconfident. And I'm talking about the models, not the people in deep learning. So the models tend to overshoot confidently. With this approach, you tend to be able to be more representative of the true uncertainty of your problem. Conditioning on class probabilities has also a big benefit, which is you can now do counterfactual analysis. So you can basically start to reason about the uncertainty in your system by saying, oh, you said it's like 25% pedestrian and 75% car. What does that even mean? What if it was 50% pedestrian? What if it was 75% pedestrian? And you can start to basically plan for different contingencies that include contingencies about your own state, about your own belief, about your own mistakes. And that's really important for a safety critical system to know that I might be wrong. And if I'm wrong in this way, what might happen? And again, can be used also for robustness analysis. And what we show is that these counterfactual predictions interpolate smoothly in the space of input probabilities. So to conclude, I hope I convinced you that bridging the perception control gap is basically centered, or at least from my perspective, on prediction. And it's hard. I would say, duh, but it's necessary. There's no shortcuts. And again, I'm saying that coming from a machine learning, deep learning context. And so why is it hard, and what are the problems we have to solve? I mentioned human intent. It's latent, but can be inferred for context destinations. It's dynamic. That's why using structured generative models is important. Producing uncertainty, very important, big focus in perception and prediction, but also consuming that uncertainty, making sure it's useful in the right representation is also important. And I think I'll leave it at that. And I'm happy to take questions if we have time, otherwise the panel.
Great, thank you, Adrien. Let's thank the speaker. And let's again give time for one question, a burning question. Okay. Okay, great. So let's see. Let's review where we are. Thank you, everybody, to all the speakers. The talks were fantastic and very provocative, and also represented, I think, not only a diverse slice of research, but a diverse range of perspectives and opinions on where the hard problems are. So that is exactly what we were going for. What the heck? Let's thank all the speakers once again. And this will kind of close out the live speaker session. So now we are going to have our panel session with our live speakers. The speakers once again are Amanda Prorock, David Fridovich-Keil, Saurabh Gupta, Rohan Chandra, and Adrien Gaidon. I think everybody's here. I'm going to assume everybody's here. So I was taking notes while listening to everybody's talks, and I wanted to try to pull out the main themes that I was hearing, and especially points that seem to be points of focus, but points in which different speakers took different stances. And I think one of these themes has to do with representation, environment representation. I think that this is one of the real keys to enabling multi-robot interaction, and especially to enabling multi-robot interaction across the perception control divide. what is the right representation that can be produced through the course of a perception stack and then ingested into a control and planning stack? And is that linear model even the right way to think about it? So I'm going to open that question up just as kind of a topic. Share your thoughts. What is the right representation? Have we found the right representation? What are the things we should focus on? And I'm going to kick it back to Adrien, our most recent speaker, because I think he has quite some interesting thoughts on this. And then I'll kind of kick it around the group, and feel free to make this a free-form discussion. You know, anybody on the panel who has thoughts, go ahead and speak up. Adrien, what are your thoughts?
Yeah, that's a great question. I think it's a question that's also picking up a lot of steam in the reinforcement learning community and many different communities, which is, it's all about representation, which is great because that's what computer vision does. I think the question is, the really interesting, so there's some interesting questions like very specific to domain, which are, is it better a non-parametric representation in terms of like occupancy grids and stuff like that, which are very flexible, and people like Raquel Ortazun, for instance, have been pushing that idea quite far across the full like learning stack for the full sensory motor loop. But there's some issues with that. I mean, there's some benefits and pros and cons to everything. The other one is agent-centric or object-centric, more symbolic in nature, which is also common in prediction. And graph networks are also very exciting about that. Reasoning in terms of dynamics, being object-centric is also something that's picking up. And these kind of like are a little bit opposed, I would say, at least in terms of data structure. So the jury is still up on that from a very technical standpoint. There's a more like also in more general scientific divide that's difficult, which is task specific or agnostic. And that's really tough also to think about, because when you think about machine learning, you have like, oh yeah, discriminative learning, your representation is some latent vector that is useful for you to optimize for your given task. But as I tried to kind of mention, an abstraction is kind of needed. So representation is more than just something useful. Usefulness or optimizing the direct end cost is not the only desiderata. But how do you specialize? How do you generalize? How do you scale? How do you think in terms of continual learning? How do you think in terms of lifelong learning? So I think like the place of the task in the representation is also a very big open question with a lot of exciting research all over the spectrum, basically. So yeah, I don't have an answer. We do have some choices that we make for different reasons, but I think scientifically it's an absolute great time to be asking that question.
Totally agree. Okay, good. I'm curious, maybe I'll go over to Saurabh, who, you know, I saw representation was something that was floating. I don't think you used the term necessarily, but that was floating around quite a bit in your kind of traversability maps and this kind of robot navigation, direct vision to navigation work.
Yeah,
looks really interesting. Yeah. So what are your thoughts on representation?
Yeah, I think this is this is the heart of the question, right? What is the right representations that agents should be building? And I think just to counter Adrien a little bit, I think by the way, I'm kind of on board with what you are saying, Adrien. I mean, and in fact, my talk was roughly in that space, which is that we're not throwing out the structure that classical robotics has proposed, that maps are important. That's kind of roughly a theme that we have been pursuing in our research as well. But I think we should realize that whenever we introduce a representation and whenever we make some choices through human design, I think we should be open to the possibility that those choices are suboptimal, right? And I think that's kind of what we have tried to think about in our work, which is, yes, occupancy maps are great, right? They allow you to do path planning. That's a fantastic ability, which is, you know, right, which a LSTM, like a fully, it's hard to imagine that they will be able to learn that, although they are also universal computers or whatever, right? So I think the question is, it ends up becoming basically a design question at that point, which is how much do you want to learn and how much do you want to handcraft? And I think I will like to bring this, so Rich Sutton wrote this blog post at some point, which is the bitter lesson. And he was basically pointing out to the history over the course of history of AI that it has always turned out that in the limit of lots of compute and lots of data, simple algorithms which can use a lot of data don't have as much handcrafting, have run out, right? Now, I'm not saying that that's the position I take, but I want to basically bring that view in, which is that it's possible that there may be an answer which is beyond representations, beyond handcrafted representations. So I think I don't know the answer, and I mean, I'm trying things based on what I feel is plausible, but we'll see. Time will tell.
I'd like to hear Amanda's thoughts on this, and I'm curious about, Amanda, your work specifically in learning what to communicate between multiple agents and how that has to do with representations.
Yeah, you're giving me the right picture. So actually really interesting. So I don't have an answer specifically to your question, but I have a Gedanken experiment. So the way we think about perception these days, or representation, is as follows, right? So we have these GNNs which allow the robots to essentially interpret the incoming information. And if we want a single robot to be able to act in a meaningful way based on the incoming information from multiple robots, what that means for our representation, or of what other robots are perceiving and sending, is that representation has to be meaningful when it arrives at a robot, because that robot is going to be stitching that together. Now, the theory actually tells us, the theory from graph neural networks that we've been building on tells us that those incoming feature vectors, they're summed up before they go through a nonlinearity. So the decision that we make on what kind of representation we have all the way downstream in the task, right? That's the first decision we make, actually has a big impact, because that information is not only going to be compressed, but it's going to be summed up together, and then it's going to be passed through a nonlinearity. So these are the kind of design decisions we have to think about when we're like, okay, is it going to be what is it going to be that we're going to essentially, what information are we going to feed through this pipeline? And what is the impact of that design decision going to be on what the robots at the end of that pipeline are going to be stitching together to, compose this worldview that they then base their decisions on.
Awesome, thanks, Amanda. I see David and Adrien both have some comments to make. David, do you want to go ahead and go first?
Yeah, sure. Thanks, Max. So I guess I just bring up two things that haven't been talked about yet. I guess the first one is when you're like an engineer implementing one of these things, like for a self-driving car company, in Adrien's case, for example, or I think at least having been in that role myself, at least what was constantly going through my head was I got to be able to debug this when it breaks. Like inevitably, every night I'll get logs of failures, and I'll have to go back and figure out, like at the stand-up meeting the next morning, what broke. And so that's like, the reason we build modularity into the system, and the reason we all learn that in like the first CS class we take, is because it allows us to debug. So I think we have to be really careful if we talk about throwing away modularity, because it just makes it a nightmare to debug practically. So I get some of the arguments folks have made, but I think that's a potential pain point. The other thing I'd mention is coming from control theory and optimal control, an important decision we have to, or an important part of the problem we should be aware of is overall efficiency, and particularly the efficiency of control design that's allowed by the representation. So for example, if the representation is just a single like certainty equivalent mean of a Kalman filter or something, then we know what to do with that. We plug it into an optimizer, it spits something out. Optimizers for optimal control can be pretty darn fast. So that's a pretty efficient representation. On the other hand, it's missing a lot about uncertainty, as we heard about. So I think this is kind of the crux of the problem is, how do we come up with an efficient representation, or a representation which is sufficiently informative but allows for efficient control design? So I think that's quite important.
Yeah, definitely. That's this not only what does the perception stack spit out, but what would the control stack like to ingest? What should be the format that's useful for control? So Adrien, what was you had something to respond to?
Yeah, so first of all, I completely agree with what David said. Absolutely +1 on everything there. I think, like to Saurabh's point, I think the bitter lesson was really interesting. I think I'm looking past this, like what's going to happen next, right? Because it's like the world is not black or white. And I think one of the things I'm really interested in is like machine learning in the real world, and it's always gray, right? And what's really interesting in machine learning in the real world is machine not learning. because you could learn everything. You could just throw everything, throw data at it. And a lot of, actually, that's the power of machine learning, is that a lot of problems can be actually very well formalized as f of x equal y. And then the main problem is just, where do I get my xi, yi's? You know, what laws do I use? This kind of stuff. And I think that in the real world, again, you know things. For instance, physics exists. So you don't want to be revisionist history, you know, like Newton never existed in the first place. So the hard part of machine learning today, I think, is really, how do we marry what we know for a fact, right? Not what the designer thinks is the right thing to do. And how do we explicitly do so? Because if you don't do it explicitly, you do it implicitly. And if you do it implicitly, that's what we call bias. And that's where you get racist computer vision algorithms and all these kinds of nasty things, which is basically leaking through the data, right? Leaking through the human, because the humans are always there. The real world is always there. And if we are like abstracting things too much in overleaf in latex equation, then bad things happen in the real world. So I think that's why, for me, this conclusion of like, oh, what should be learned, what should not be learned, is structure. Structure should not be learned. Certain things you know for a fact about your domain, like physics, for instance, in robotics, should not be learned. But then the challenge, the technical challenge, is how to integrate it. And that goes with what David's point was, which was like, it's sometimes hard, and sometimes you make simplifying assumptions for computational reasons. But that's where research is exciting, is how do you combine what you know with what you need to learn.
Yeah, that's great. I'd love to hear from Rohan on this, in particular, Rohan, because I think of all the representations we saw, yours was the simplest, just a graph. And I think there's huge power in that, just distilling only the basic information that you need, because then you can really focus on scalability and speed and online performance. So Rohan, what are your thoughts?
Yeah, so so there are two parts. So one is the question that you just posed, and I had like a separate tangential thing to discuss with Adrien and Saurabh. So regarding the thing you said, right, the graph, it's probably the simplest thing that I tried. It worked, but it still doesn't have a learning component to it. It's still mostly a classical model. I did try regression on it. I did try some classical machine learning algorithms that still worked, but what I had is a very deterministic classical model. So given a simple graph output, I apply a couple of formulas and it worked just fine. Yes, that is simple. But what I had in mind for Saurabh and Adrien is that at UMD, like me, Dinesh, and a couple of other people were collecting a huge data set of Indian driving data, you know, and it has all sorts of labels like behavior labels like rule breaking, cutting red lights, and you're driving on the opposite way. Motorbikes are zigzagging through the traffic. So it's essentially a data set dedicated to Indian traffic. And when we tried perception algorithms on it, segmentation, tracking, prediction, what have you, they all failed spectacularly. And that's why I included that bullet point in my talk, that perception fails almost automatically and immediately. So what kind of, so Adrien, you were talking about, you know, needing explicit versus implicit structures. So what kind of explicit things do you think autonomous driving would need in terms of perception for those kind of driving scenarios? Because we mostly know what we need in terms of US traffic, or we're not there still, but we sort of are. But we completely are not in terms of countries in the East. So what do you think is some of the explicit structures that we need in terms of representation to enable perception better over there?
It's interesting. This makes me think a lot, Adrien, of what you said about the perception stack being able to assess its own confidence in its results accurately, right? To express how uncertain it is about a result in either an Bayesian way or some other way. And this also seems related to being aware of out of distribution operation, right? If you're trained on US traffic scenarios, you would hope that some part of your perception stack would say, wait, I'm in New Delhi. This is very different than what I was trained on. You know, use my results with caution. So maybe Adrien, quick response, and then we'll go over to Saurabh, who's had his hand up for a while.
Yeah. I mean, you opened the Pandora's box with your question, Mike, about the representation. That's the core question. So everybody has some opinions about it. That's great. Yeah, Rohan. So to answer briefly, this is how self-supervised learning works today. which is how do we devise objectives that correspond to loss functions we can pay on the raw data. And so structure here in this problem could be just as much like physics of light. So for instance, how a lot of the work we do in the team is self-supervised depth estimation. So if you know your camera, like basically geometry exists. So if you know your camera is well approximated by a pinhole camera model, and you know a little bit about physics of light and projective geometry, then you can actually use motion as a source of supervision. And that source of supervision comes from projective geometry equation. It's literally an equation of warping and then the photometric loss. It makes some assumptions, so it's not perfect, but like you can use geometry as a source of supervision and self-supervised learning. You could use physics. You could use things like, you know, I assume that even in Indian driving, even at close calls, there's non-interpretation constraints that are not violated too often. So I think there's the ground plane, it's there. So gravity has a direction. This is all used, for instance, for object-centric representation and unsupervised learning setups. So there's a lot about the world that you know, that holds in generality. The real question is, for instance, self-supervised learning is how do I capture it into a self-supervised objective? Is that the right inductive bias to learn object-centric representations? For instance, do objects emerge from that set of constraints? And so that's like, there's a lot of knowledge. I mean, that's the thing, is that we're 21st century. Humanity has so much knowledge. It's actually, that's the hard thing. And that's why, myself included, like we tend to think, oh, it's just too complex. Let's just learn everything, f of x equal y. But actually, I think for real world solutions, you need to embrace that complexity and go through the slow slog of like gradually incorporating prior knowledge with machine learning. And again, that's just to make machine learning more grounded and embodied, which is important for sensory motor systems, right? Again, it's very different than the tech world of ML. We're talking robots, right?
Saurabh, what do you have to say?
Yeah, I think I want to make 2 points. I think the first one is about bias and so forth, right? Now, I will admit there is algorithmic bias, which is, you know, it might just be in the design of what we are building in, but a lot of it comes from data. And I think my argument there is that we don't need, I mean, and one way to get rid of this bias is to collect diverse data, right? So I will be very surprised if something works on Indian roads, which doesn't really collect data from Indian roads. So in some sense, I think the way I see this going forward is that data sets will just keep getting bigger. And that is going to be essential to get computer vision to work on diverse things. And so I think we need to do something with data at the very least. We might need to do we very likely need to do other things as well, but we need to do data. We need to get more and more diverse data. And now I think all of this bias and computer vision not working and all of that, I think it gets exacerbated if you also put human in the loop when they're designing models, because then they're going to build in even more. So when we're trying to build in more structure, I would say that that's the bias that we're putting in. And in some sense, what Adrien argued to me seemed like that he's arguing for removing the structure so that you can remove the bias and get these algorithms to work more generally. Okay, so that was kind of my first point. My second point, which I wanted to make, was about physics, I think, which Adrien very nicely pointed out. I think physics is again a thing which we believe we understand, and we do it very well for rigid objects, right? But once you start involving contact, once you start involving deformable objects, once you start involving fluids, I think we know quite a lot, but in order to instantiate those physics-based models in the real world on real cloth, for example, you will, associated with the model also comes the sensing, right? I now need to know exactly what's happening in each part of my shirt, for example, if I want to, fold it. And that's really, really hard. And in some sense, maybe, and as a human, I don't really understand all what each atom in my shirt is doing, yet I can still manipulate it successfully. So maybe this is an argument for we need less structure. I don't know. And that's kind of what I wanted to say, but we'll see.
I love it. This is what these panels are for. The diversity of opinions is great. I mean, nobody's right or wrong. These are all really insightful comments. I want to steer the discussion a little bit away towards from representations towards the more of the multi-agent aspect of this workshop, and ask, I think probably Amanda and David will have more to say on these topics. What is the role or the necessity of communication in multi-agent interactions, for example, crowd navigation or autonomous driving in traffic? I'm just curious on your thoughts. Amanda, we'll start with you. Let me just give the context. In autonomous driving, it's generally assumed right now in autonomous driving research, and certainly in autonomous driving practice, that there is no agent-to-agent communication, that the autonomous car's job is the same as the human driver's job, which is to be an island of perception and action that's isolated from the world as far as data goes. But that doesn't have to be the case, right? So is there a strong argument to enable vehicle-to-vehicle communication?
Yes. So for me, there are 2 points, right? The first thing that communication does for us is it allows us to essentially pass on information about unobservable values, right? So if another vehicle sees me, that other vehicle will have, unless there's some clear sign I'm making, will have to ask me what my intent is, for example, right? And that is something that I will communicate to that other vehicle explicitly. So anything that is not observable explicitly has to be communicated. So that's number 1. And number 2 is you can leverage communication to see around corners, right? So if you think about autonomous vehicles, that's my go-to example. You have one around a corner, sees a passenger going over a crossing, the other one's coming. It's like obvious, right? That vehicle is going to tell the other one, hey, you know what? This passenger shouldn't be going across because it's red for the passenger. Watch out when you come around the corner, slow down. I mean, it's a no-brainer for me, right? And more formally, this example, it just boils down to simply saying, right, robots that don't have a bird's eye view of the world, they're operating under partial observability of the world. And one way of getting around that is by stitching together information that is being propagated through a network, right? And that's why we're so keen on graph neural networks, because that is exactly what they're doing for us. It's the data-driven way of approaching this problem.
Yeah, absolutely. What about the fact that we'll always have humans around and humans are not Wi-Fi enabled? Yes.
Yeah, no. So, I mean, I think that there are a couple others in the panel that can speak more to the human side of things, but all I can say is that, the more sensing you have in an environment, and sensing being, it can be other vehicles, or it can be CCTV, or it can be roadside units, etc. Right? This is not a far distant future. I think this is just around the corner. That sensing, you're gonna communicate that to devices in your environment, and that those devices will make sense of that information. I think it's myopic to think that one autonomous vehicle based on its camera, like this, looking at a human doing something, is going to have to make up its mind all by itself what that human is going to be doing. That is not the future. The future is that vehicle integrating information from a bunch of sensors that are all around us. I think that's the way to think about it.
Totally agree. Yeah, yeah. And it's it makes a problem that's obviously intractable, at least hopefully a little bit more tractable, right? At least if you're taking the perspective of multiple autonomous vehicles watching the human, you might have a better hope of, and not only that, but the experience combined of all those cars' history, that you might have a better hope of predicting where that pedestrian.
I mean, yeah. So the research problem doesn't become easier, but I think this is kind of the challenge that we have to tackle, and I think this is the right way of thinking about it, in my opinion.
Thanks, Amanda. David, what are you thinking? How does this tie into game theory?
Sure. Yeah. So I guess I definitely buy that communication. More information is generally better, and communication, I think, has tremendous opportunity or potential for improving efficiency. That video that Amanda was showing is, I think, very good motivation for that. But on the other hand, I think it's I'm not sure how realistic it is to, be thinking that, for example, Waymo is going to be telling, their intended paths to cruise, for example. Like, it seems to me like there's some intellectual property issues, or I don't know if IP is quite the right term, but it seems to me a little bit, let's just say I'm skeptical. And then, suppose that they would do that, or even that they're required by law to do that, or something like that, then there are just a can of worms that get opened. Like, what about security issues? Could a hacker get in? What about deception? Maybe Waymo can, I don't know, insert some malware into their you know, maybe they can doctor their communications to gain an advantage somehow, or somebody else can. So I think there's just a can of worms that get opened, and you know, I think that's our job as researchers to think hard about those. But I guess it's another reason for me to be concerned. And then I guess just maybe two things I would mention, kind of getting towards this issue of seeing around corners, which I think is a really good, again, motivation for the potential upside of communication. And I think all hope is not lost in the isolated case, in the no communication case. So, you know, clearly you and I and everyone else who drives does a, you know, reasonably decent job. Of course, we could do better, we could be safer, but, you know, somehow we do okay with this. And I think there's a few papers that come to mind, recent papers, that I think do a spectacular job of mathematically pinning down, you know, how we can automate some of this reasoning. So, like, I was just in the main conference poster session this morning, and there's a great paper from Princeton, from Jaime Fizek, that talks about how to encode basically occlusion awareness using game theory. And I think they do just a beautiful job of explaining how to do it. I think there's a lot of questions that they raise, but I think it's a really, really fine start. And another one would be from actually one of Saurabh's colleagues, Katie Driggs-Campbell, a couple of years ago, put out a paper that essentially said, hey, if you're approaching, let's say, a crosswalk or an intersection, you can't see, you know, there's some occlusion, maybe there's a truck in front of you blocking the crosswalk, but they're stopped and they have a green light. Chances are there's something making them stop. So you could use that as sort of some sort of virtual sensor, I think is what they called it. I think there are some, you know, good directions that people have found, I guess is what I'm saying.
That's great. Thanks, David. So let's wrap up this panel session. Amanda, you are going to have the last word. You also had the first word, so that's a nice bookend for this whole session. Amanda, what are your last thoughts?
I actually it was really short, and I actually it was more a question for all, you know, the folks on the panel who have a lot of experience with machine learning. And it follows up on something that David said, because you said, and this is what I learned when I was studying Kalman, you know, filters way back then, more information is always better, right? Because when you have sensor fusion, your uncertainty decreases, right? But look at what is happening to Teslas. They're removing radars because radar information, according to them, is not helpful, is not more information. And I think that we're kind of moving into this era where, you know, sensor fusion with machine learning based perception models is not the same anymore as what we've learned when, you know, we read Turin's book and all that. That's the school we're coming from. And I think things are changing. And I don't really fully understand. I don't have an answer to this question, but I think talking about multi-agent systems and sensor fusion coming from different robots and is it helpful or not, I think is a really, really important question to maybe think, to write down and talk more openly about.
Very provocative. I like that. We're missing maybe some theoretical tools to understand when is more information actually worse. All right, folks, wonderful. The panel discussion was so fruitful, and so we touched on so many great ideas. I really appreciate the participation from all the panelists. Let's give a hand to all the panelists. And I'm going to hand the workshop over to my co-organizer, Negar Mer, who's going to lead the lightning talks in the poster session. As you all know, we are running a little bit late, but there's no hard stop on our session here, so we can go ahead and proceed past one. Negar, the floor is yours.
Great, thanks, Mac. And thanks to the panelists for the great talks and great discussion. This was really insightful. So I think now it's time for us to hear from our lightning talks. And we are going to start with Victoria from Stanford. And I think this work is actually very related to what Amanda was mentioning regarding asking for information from different sensors. So is Victoria in the audience?
Hi, that's me.
Oh, great. Go ahead, Victoria.
Oh, okay, cool. So hi, my name is Victoria, and in the next 2.5 minutes, I'd like to introduce to you a project I've been working on at Stanford in collaboration with Ford Motor Company. The title of this research is Infrastructure-Enabled Autonomy and an Attention Mechanism for Occlusion Handling. And next slide, please. Next slide. Hello? Oh, thanks. So the question we are trying to answer is, yeah, that's the right one, thanks. The question we are trying to answer is how to improve decision-making in autonomous driving around occluded areas with the help of infrastructure sensors. So cities and communities such as like Palo Alto, which is like right around where I live in California, started investing in infrastructure sensors. So those will be like little cameras on top of traffic lights. And they gather data about the environment. And so because they observe the same scene as an autonomous vehicle, but just from a different angle, we have the opportunity to close our perception gap here. So here's the catch though. We have to process all this additional data from each sensor in our environment. And it's so evaluated, right? So like localize and classify agents. Oh my God, my laptop is dying, sorry. Excuse me, localize and classify agents, and then fuse the information, as you might see the same car from just different angles. All this computation has to happen on board in real time. So by framing the problem as a POMDP, where querying infrastructure sensor data is a data gathering action, we try to reduce computational complexity while maintaining the competitive performance of an omniscient agent. So if we look at the POMDP definition on the slide, we find that we added a sensor selection task to the action space alongside the navigation. The observation of each time step is a noisy position of all the agents perceived in the scene. And so perceived in the scene by either like the onboard perception system or the infrastructure sensor that we queried. Next slide, please. Thanks. Our experiments ran 3 scenarios with 500 simulations, each in like 4 different action modes. So we are comparing the attention mechanism. So like that's just our method to an omniscient actor, which has access to all the sensors at each time step, and a heuristic, which queries the closest sensor, and then a blind agent, which just doesn't have access to any of them. The scene depicted below has 5 total interactions, so 2 pedestrians, then a car merging with another car, and then another pedestrian at the very end. I think the main takeaways are simply that infrastructure to vehicle communication can actually help like improve our driving behavior. As we can see that, for example, the collision rate for a blind agent is 45% versus ours, which is like 8.5, which is rather competitive with the 6% collision rate of an omniscient actor. Also, our method seems to be keeping up well in terms of jerk with the omniscient actor while maintaining the runtime of the blind actor, which actually is just not accessing any of the infrastructure sensors. So I think this was 2 minutes and a bit. So thank you for your attention, and please check on my poster if you have time.
Great, thanks, Victoria. Thanks for the great talk. So in the interest of time, I think we should reserve questions for the poster sessions, and we'll move to Haruki from Stanford.
Hello, everyone. I'm Haruki Nishimura from Stanford University, advised by Max Schweger. So in today's poster session, I'll be presenting our work entitled Risk Auto-Tuning Digit LQR, and this is a joint work with Nigar, Adrien, and Mac. Next slide, please. Thank you. We consider the problem of crowd robot navigation as a stochastic optimal control problem from the robot's perspective. Here, the stochasticity comes from the uncertain human motion in the future. And the issue we'd like to highlight is that this probabilistic behavior model is almost always not a perfect one. So on the left, we have a simplistic Gaussian model for the human motion, which fails to capture the multimodality of humans' decision-making process. And on the right, we have a more complex, possibly learned multimodal motion model. So ideally, we'd like our planner to utilize this complex distribution, but there's a computational issue that there is a need to collect a lot of samples from this distribution to capture all the important pieces of information about this distribution. And this can be quite computationally intensive to run in real time. So our approach to this issue is to base our planner on the standard Gaussian distributions as on the left for computational efficiency, but also make the planner aware that the model of the distribution is not perfect and that there's a distributional model mismatch. Next slide, please. And it turns out that this is a tractable problem, even for nonlinear systems with non-convex cost functions. And specifically, this can be done by optimizing the entropic risk measure that Adrien already explained in this talk, but this time along with the risk sensitivity parameter. So in conventional risk sensitive optimal control, this theta is a fixed constant, but we propose a way to also optimize this risk sensitivity parameter together with the control policy. And it turns out that this makes our planner robust to the distributional model mismatch. So the algorithm is an extension of the well-known iterative LQR type controller, which is computationally efficient. Next slide, please. Next slide. Yeah, thank you. So in simulation study, we compared our algorithm with baseline methods and showed that our planner is safer in presence of the model mismatch. So if you're interested in more details, please come see me during the poster session. Thank you.
Great, thanks, Haruki. I think next we have Abhinav, who's going to talk about segmentation, which I think is very relevant to semantic segmentation, very relevant to the discussion we've had so far. I saw Abhinav was in the audience. But he is not here anymore.
See his name in there.
Yeah, I can see him too, but.
All right, should we move on to Zhanteng and then we can go back?
So let's move to the next talk and then we'll go back to this one. So Zhanteng from Temple University, can you go ahead?
Okay. Hi, everybody. My name is Zhanteng Xie, a third-year PhD student at Temple University. I'll talk about our recent work called Safe and Fast Navigation Through Cloudy Dynamic Environments. This work was done by Pujie and I under the guidance of Dr. Dames. In this work, we combine deep reinforcement learning with the velocity obstacle concept to create a control policy called DRL-well policy to enable a robot to safely and quickly navigate through environments filled with both static obstacles and dynamic pedestrians, such as in this picture. Next slide, please. Okay, in order to create our control policy, we need to consider two key problems. One is how to deal with sensor data to get useful information, especially process the pedestrian information. The second is how to design a good reward function to guide the robot to avoid cloudy dynamic pedestrians. For the first perception problem, we propose a novel pre-processed data representation, which encodes pedestrian kinematics and the LiDAR history scans. We feed this pre-processed sensor data and the goal information into our DRL network and use PPO algorithm to train it. Finally, we get our control policy. In order to train a good policy, we propose a novel heading direction reward. We are using the velocity obstacle model to guide the robot to learn how to tune its heading direction to actively avoid the pedestrians and also move towards the goal. Finally, let's look at our navigation results. Compared with other baseline policies, our control policy has both highest success rate and LG speed in clouded environments and unseen environments. Okay, next slide. Yeah. Thank you for your attention.
Thank you very much. I think now we have our last talk. Abhinav, go ahead.
Yeah. I'm just not able to switch on my video.
That's okay, no worries. I think Philip has shared your slides. Can you see your slides?
Should I start?
Yeah, go ahead.
Okay, so on the first slide, like we propose a new network architecture for real-time semantic segmentation. In this work, like the paper title is Semantic Segmentation with Multi-Scale Spatial Attention for Self-Driving Cars. So we propose a new attention module to encode more contextual information and enhance the receptive field. So like our main goal was to balance the speed versus the IOU or the intersection or union trade-off. So in this paper, we used like dilated convolutional layers in the downsampling part and use at-risk convolution for the upsampling part. And we use concat operator to merge the features. And we use a very own design attention module to encode the channel-wise information to enhance the receptive field. And we use Cambridge dataset and Cityscape dataset to benchmark the performance of our network using mean accuracy per class and IOU as the evaluation metrics. Our network architecture, can you just show the next slide? Next slide, please. Yeah. So our network architecture looks like this. And can you show the last slide? Yeah, so the final segmentation results, like which we got using our network, the complete network architecture details and the ablation studies, the loss functions which you used for the optimization details can be found in the paper. I've also open sourced the code, which can be found in my GitHub repository. Yeah, so that's from my side.
All right, thank you. Thanks very much. So I think for those of you who want to know more about these great works and want to ask questions, it's time to start the poster sessions, which I think are going to happen through breakout rooms. Philip is going to enable them, so feel free to join these breakout rooms to know more about these networks.
Yeah, so I guess I will be giving all the presenters screen sharing privileges and opening up, like we have 4 posters. So I'll open up 5 breakout rooms, 1 for just being in if you want to talk about other things. And you should be free to swap back and forth between the breakout rooms as needed. I guess with the breakout rooms, there'll be 5 of them. So I guess can the first speaker, Victoria, go in room 1, the second speaker go in room 2, etc. So that way we just kind of have a clear order of who's going in which room to share their posters. All right, and I guess with that, this is also kind of ending the group element to our workshop. So thank you everyone for attending. This has been, a great turnout. I think our peak was around 60 people here, so that's really good turnout. Thanks for the great discussions and questions from all the panelists and speakers and everyone. So thank you.